So let's start with a simple topology to illustrate how spanning tree works. Why would you require spanning tree in a switched network? So in this topology we have host A connected to switch 1. Switch 1 in turn is connected to switch 2, and switch 2 has host B connected to it. So very simple topology. Now if the link went down between switch 1 and switch 2, host A wouldn't be able to communicate with host B and vice versa. So you're probably going to want to implement some kind of redundancy between those two switches by adding an additional link. So that's great because you now have a network redundancy in case one of the links goes down. However, that introduces problems in a switched environment. It's generally recommended in networks today that you implement some type of redundancy. So in this example, you have two links between your two switches, but that will introduce additional problems which we'll now discuss. Let's assume for the moment that the switches have just booted up and their MAC address tables or CAM tables are empty. And to help explain this issue, let's add MAC address tables to the topology so that you can see how the MAC address tables are updated when traffic is sent from one host to another. So let's assume that in this topology the switches have just come up. In other words, they've been rebooted or powered up, and the MAC address tables or CAM tables are empty on the two switches. Now when A sends a frame to B, the destination address in the frame will be B, and the source address will be A. So A is sending a frame to B, and when it arrives at switch 1 will read the source MAC address of the frame, and the switch will see that the source address is A. The switch will update its MAC address table to state that A can be found on port 1. MAC address B, however, is not in the MAC address table, so the switch will flood the frame out of all ports except on the port on which it arrived. So in this example, the frame will go out of port 2 as well as port 3. It does that because it doesn't know where MAC address B is. Now this is obviously a very simple topology. In this example, the frame is only being sent out of 2 ports of the switch. However, if the switch had many ports, let's say 96 ports, an incoming frame on one port could be replicated out of over 90 ports on that switch. That increases the amount of traffic sent in your network quite dramatically. So in this topology, what does switch 2 do with the frame received on port 1? The source address once again is A, and the destination address is B. What will the switch do with the frame? Well, firstly, it's going to update its MAC address table to state that A can be found on port 1. And then it's going to flood the frame out of all ports. So it'll flood it out of port 2 as well as port 3. So in this example, host B will receive the frame from host A. However, the switch also receives the frame on port 3. And this is where it gets a bit confusing. Where is A from the switch's point of view? Is it on port 1 or is it on port 3? So in this example, it's going to update its MAC address table to state that A is on port 3 because the frame, in our example, arrived on port 3 later than on port 1. So it's going to update the MAC address table entry to state that A is now available on port 3. The switch will also flood the frame out of all ports. So it's going to flood it out of port 1 and out of port 2. So host B has now received the frame twice. Once from the original frame that arrived on port 1, sent to host B, and secondly for the frame that arrived on port 3. So this can get confusing for end devices because they're receiving the same frame multiple times. The MAC address table is also changing. The first frame that arrived on port 1 allowed the switch to update its MAC address table to state that A can be found on port 1. However, the frame that arrived on port 3 now indicates to the switch that A can be found on port 3, so the switch needs to update its MAC address table to state that A can be now found on port 3. So this introduces instability in the MAC address table. So we have end devices receiving frames multiple times, and we have MAC address instability because the switch thought that A was available on port 1, but now sees that it's available on port 3. But it gets worse. When the frame arrived on port 1, the switch updated its MAC address table to state that A can be found on port 1, but it also flooded the frame out of both port 2 and port 3 in this topology. The frame was received by host B, but in addition, the frame was sent back to switch 1. So switch 1 has received the frame that it sent to switch 2, and switch 1 now updates its MAC address table to state that A is available on port 3. Now when switch 1 receives the frame, it not only updates its MAC address table, but it also floods the frame out of all ports except the port in which it arrived. So the frame arrived on port 3 and is flooded out of port 1 and out of port 2. So this gets confusing for host A, because it's receiving the frame that it originally sent. But not only is A receiving the frame that it sent, switch 1 is also sending the same frame back to switch 2. And what is switch 2 going to do with the frame? It's going to flood it. So it's going to send a copy to host B. Host B has now received the same frame 3 times, but it'll also send the frame back to switch 1, as well as updating its MAC address table to now state that A is on port 1. So originally, when it received the first frame, it thought that A was on port 1. Then when it received the frame on port 3, it thought that A was on port 3, and now it thinks that A is on port 1. So we've got a lot of MAC address instability in the MAC address table. Host B is receiving the same frame multiple times, but the biggest issue here is that the frame gets sent back to switch 1, gets flooded again, gets sent back to switch 2, and this process continues over and over again. We have a loop in this topology with the frame being duplicated and sent round and round and round between these two switches.